resistors in a combination of series and parallel configurations. The combination circuit is sort of like the boss at the end of the first level of circuit analysis. Together, we'll tackle this bad boy using the principle of equivalent resistance and Ohm's law. We'll determine the voltage across, current through, and power dissipated by each of the resistors depicted in this circuit diagram. Okay, the first thing we always do when solving a physics problem is to draw a picture. But with the circuit already drawn, we just need to apply a few labels. We'll label the positive and negative side of the battery, as well as the junctions. And if we had more room on the circuit diagram, we'd also label the unknown currents, but we'll come back to those in a little bit. Now, before we take a crack at this circuit, I recommend that we replace this empty leg with a dummy resistor, a 0 ohm placeholder that will make our analysis a little simpler. This step isn't necessary for seasoned veterans of circuit analysis, but I find it to be helpful for beginners. Alright, to analyze a combination circuit, we'll use what I call the break it down, build it up method. We'll break the circuit down piece by piece, determining equivalent resistances until we have a single equivalent resistance for the entire circuit. Then, we'll build it back up piece by piece using Ohm's law until the voltage across and current through each resistor has been determined. Okay, let's break it down now. We'll start by redrawing the circuit so that series and parallel relationships are readily apparent. We'll write first redraw because there will be quite a few. The basic idea for our first redraw is to convert our circuit diagram, which has kind of this loopy current path, clockwise from positive to negative, into a unidirectional one, left to right. I find it useful to imagine grabbing the positive side of the battery with your left hand and the negative side with your right, then breaking the battery apart and stretching the circuit out onto the page below. So we put the positive side of the battery here on the left and translate the rest of the circuit. After leaving the positive side of the battery, the current encounters the 100 ohm resistor first, so we'll write that here. And thereafter, the current encounters junction 1. There's a three-way split at junction 1, which means these legs are in parallel, so we'll draw them geometrically parallel below. So this top leg has a 50 ohm resistor, and a 250 ohm resistor follows it, so they're in series. And the top leg terminates right here, at junction 2. There's another leg that begins at junction 1 and terminates at junction 2, and it comprises this devilish diagonal resistor. Despite its menacing appearance, this resistor is just connected in parallel with the top leg, so we'll draw it simply spanning the gap between the two junctions below. After junction 2, we have this bottom leg with our 0 ohm resistor. We'll put that to the right of junction 2 here. And then we get to junction 3. Between junction 1 and junction 3 is a single 300 ohm resistor, so it is in parallel with the 4 previously drawn resistors. We'll depict this by dangling one long leg from junction 1 and junction 3. Finally, following junction 3, we have a single 150 ohm resistor leading us home to the negative side of the battery. So we draw the 150 ohm resistor here and finish with the negative side of the battery on the right. And that, my friends, is our first redraw. You can see what I meant by breaking the circuit apart and stretching it onto the page. Now we can easily determine our first equivalent resistance. We'll start with the resistors that are furthest from the battery and determine their equivalent resistance. So, working inward from the positive and negative sides, we find that the 50 and 250 ohm resistors fit the bill. If you're ever unsure where to start, resistors in series are always a good bet. So the equivalent resistance for these two resistors is 50 ohms plus 250 ohms, which equals 300 ohms. This is how we calculate equivalent resistance for resistors in series. Simply sum their individual resistances. And this brings us to our second redraw. We'll redraw the entire circuit, but in place of the 50 ohm and 250 ohm resistors, we'll draw a 300 ohm resistor, like so. Once we finish our second redraw, we again turn our attention to the circuit diagram and determine the resistors furthest from the battery. Moving inward from the sides of the battery, we find that these two resistors are the next to be combined. We calculate their equivalent resistance differently because they're not in series, but in parallel with one another. So for our 300 and 200 ohm resistors, REQ equals 1 divided by 1 over 300 ohms plus 1 over 200 ohms, which equals 120 ohms. So for resistors in parallel, the equivalent resistance is equal to the reciprocal of the sum of the reciprocals. Okay, moving on to our third redraw. Here we'll have the same circuit as depicted in the second redraw, except that we replace the 300 and 200 ohm resistors with their resistive equivalent, a single 120 ohm resistor. Starting to get the hang of this? If not, don't panic. We've got a couple more redraws with which to practice before we're done breaking it down. So, which resistors are next? You guessed it, the two that are in series. So we just add their resistances together. Not a very exciting equivalent resistance, I admit, but note that junction 2 will not be present in our fourth redraw. So we wash, rinse, repeat, replacing these two resistors with their resistive equivalent. And perhaps by now you've identified the next resistors to be combined, the two in parallel right here. So for their equivalent resistance, we'll have 1 over 120 ohms plus 1 over 300 ohms, which yields 86 ohms. Again, we redraw the circuit, this time replacing the two parallel resistors between junction 1 and junction 3 with our 86 ohm resistor. This redraw leaves us with 3 resistors to combine. They're in series, so we just sum their resistances, which yields an equivalent resistance of 336 ohms. Which brings us to our final redraw. We've reduced our initial 6 resistors to a single equivalent resistance, which means we're done breaking it down. If we bend our circuit back together, reconnecting the positive and negative sides of the battery, it should be clear that we're left with our old ohmic friend, the simple circuit. And as far as the battery is concerned, that's all there ever was. No matter the circuit's configuration, the battery only sees an equivalent resistance and supplies the circuit with a corresponding current. How the circuit divvies up the